Hello, everyone. Welcome to another session of RoboLaunch series. Today, it's my pleasure to introduce Professor Zachary Manchester. Zachary Manchester is an assistant professor at Carnegie Mellon University Robotics Institute, where he directs the Robotic Exploration, or REX, lab. His goal is to enable robotic systems that can match or exceed the level of agility, efficiency, and robustness demonstrated by humans and animals, especially in challenging environments. And for this, one focus of his research is building on ideas from control, estimation, game theory, optimization, and physics to develop new algorithms. And another is designing and building hardware systems to bring these algorithms to life, including legged robots, teams of networked drones, and swarms of tiny satellites. Zachary obtained both his Bachelor and PhD from Cornell University in 2009 and 2015, respectively. And before joining Carnegie Mellon University, he was an assistant professor at Stanford University, Postdoctoral Fellow at Harvard University, and worked as an Aerospace Engineer at NASA. So without further ado, I'll give the microphone to Zach.
Okay, awesome. Thanks for the intro. And I guess you guys are going to field questions during this, right? And we're going to save them for the end. Is that right?
Yes.
I will. All right, cool. So I'm going to tell you a little bit about our lab and hope that the Zoom screen sharing cooperates. Let's see, PowerPoint. Oops. And full screen. Hopefully everyone can see this.
Yeah, perfect.
Good deal. Okay, so our lab's called the Robotic Exploration Lab, and a good sort of high-level kind of tagline for what we do is numerical methods for things that move. So we work on mostly control and kind of broadly described, and we work on so how things move, how to make things move the way you want and interact with the world, get where you want them to go efficiently, all that kind of stuff. And the tools we use from that to do that are all kind of really all come from numerical optimization. So we do optimization, we write algorithms to solve optimization problems to sort of like help figure this out with computers. And so I'll tell you a little bit about at a high level kind of what we do, and then some more details on like a lot of the projects that we have worked on in the recent past, are currently working on, and that we're like getting into, and that are all kind of things that you could get involved in potentially as a risk student at CMU if you were to come here and hang out with us for the summer. And I should say too, we've had lots of risk students in my lab, and it's always been awesome. So I'm a huge fan of this program, and I think it's great. And we love having you guys. Okay, so let's get into it. So let's see. Okay, here's one of my favorite robots, Mars Curiosity. And this thing's, I was actually just at JPL like 2 weeks ago and got to see this thing up close in the Mars yard. It's super fun. But okay, so some specs, right? These things have been in space, been on Mars for like 7.5, 8 years. Again, super impressive, given this is like one of the harshest environments you can imagine. And they've gone, 20 and change kilometers in that amount of time. That sounds like a lot. That's kind of impressive. But when you divide those numbers, it's a lot less impressive. It turns out that works out to like maybe 8 meters per day. So like, like a handful of paces, right? It's like 10 steps, that you might take walking. So that's not that impressive. And you might ask the question why that's the case. And the answer is roughly that turns out these robots are not very autonomous. The way they're actually controlled from the ground is roughly, they have this thing called the Mars Yard at JPL that I meant to sneak a picture in here of, sorry, you can go look it up. But it's basically a giant sandbox with rocks and all kinds of stuff. And to figure out how to drive the rover, they look around with its camera, kind of look at the area around the rover. And then on Earth at JPL in the Mars Yard, they go and put rocks in all the same places and try to kind of like set up a clone of the environment around the rover on Mars. And then they practice driving it through that environment a bunch of times on Earth to make sure everything's good and they're not going to get stuck and all this kind of stuff. And then once they've done that a bunch and painstakingly designed and tested the plan, they uplink the plan to the rover and it executes it. So it's very human in the loop, control from Earth. And it's again not very autonomous. There's some autonomous driving stuff that they've been doing more and more, but it basically only drives autonomously when there's like perfectly level, flat ground with no rocks and stuff like that when it's easy. And as soon as it comes up to something that it will have to drive around or think harder about, it just stops and says, help me. And all that stuff done on the ground. In contrast to that, this is the kind of stuff we want to enable our robots to do from a control perspective, right? This is kind of what we're really excited about in my group is we want robots to be able to do this kind of stuff, right? Like what these mountain goats are able to do, taking advantage of, like, first of all, just traversing these really extreme environments, taking advantage of contact interactions, with the environment, being super dynamic, right? Taking advantage of all of the capabilities of their actuators, in this case, their muscles and what their bodies are able to do. But yeah, like this is, in spite of, all the progress that's been made in the last couple of decades by people like Boston Dynamics and others, we still are nowhere close to being able to do this kind of level of motion planning control in an unstructured outdoor environment, right? Like, we can do cool things in a lab setting where we know where everything is and we can plan it all out. But like if you put a robot in a completely, rugged, unstructured environment like this, I mean, you're kind of stuck. We can't do anything like this. So we're trying to get robots like that Mars rover to be able to traverse and deal with environments like this on their own autonomously. So that's like the grand plan. How do we do that? So, and apologies for there's some math here, but it's not too scary. I mean, we're going to just talk at a high level. But a lot of what we do in the lab, going back to the numerical methods optimization thing, a lot of what we do is based on this kind of broad class of algorithms and ideas called trajectory optimization. And what's going on here is you have a model of your robot, so like F equals ma, physics stuff that says how it moves, and that could be a lot of different things. And then you can have constraints. So you might have things like, actuator thrust or torque limits, joint limits, things like that, right? Limits on what, constraints on what the robot can do. So you write all that down, that's your model. And then you have this thing up here that we call the cost function. And this encodes the behavior you want. And this is something you write down. It's maybe something like minimize, fuel use or energy, or minimize time to get to the goal, like whatever it is that you want the robot to do. It might be something about, steering around obstacles, safety, things like that. You write it down in the form of this cost function. And then you basically solve this problem. It tries to minimize that cost function that describes behavior subject to the dynamics and the constraints, that's the physics, and try to get you out some kind of motion. You can do a lot of really cool things with this. And we'll show some examples. So here's, again, this is work we did a few years ago. This is a couple cool things, right? So this is a little quadruped showing it like climbing up on a step. The one on the bottom right is limping. And again, this is the way you get this out. You put in the physics of the robot. The way we get the limping out is actually by putting a cost on the force on that foot. And you're saying, I don't want to put a lot of weight on this foot. And, it's got a high cost associated with it or whatever. And what comes out of that is this very naturally, this limping gait. So you can imagine all kinds of things you might do with this, right? So, kind of automatically, if you were to like damage the robot and it had a damaged leg, all you got to do is change the cost function and put something like this in there, and now it'll limp. All kind of cool, right? So this is amazing stuff. But the problem with this is, these little examples I'm showing you that are like 5-10 seconds long, these take half an hour or more to solve, which means that this stuff right now is very much an offline thing that you've got to, sit down and like have your computer sit there for a long time to kind of reason about all this stuff and figure it out. And a large part of what we've been trying to do in my lab for the last 5 years or so is make the solver algorithms that solve that optimization problem way, way faster, so that we can solve problems like this in real time on board the robot and kind of, react to changing things in the environment and all that kind of stuff. So that's a lot of what we do. That's kind of the numerical method side. That's the problem setup that we're trying to attack. And we're trying to develop solver algorithms that can solve these on embedded computers, fast, reliably, et cetera, so that you can do it online. Okay, so this is an example. This is the first solver that we put out from my lab about 4 years ago now. It's called Altro. And this is showing it compared to kind of like a classic, like off-the-shelf solver, generic solver called IPOP that's kind of standard. And on all these kind of little toy robotics example problems, we're able to solve these dramatically faster than kind of the off-the-shelf solver, anywhere from 25x to like almost 1,000x faster on examples like this. And this is kind of getting us towards the ability to do these again on systems like this. Totally, you can do this in real time. The more complicated the robot gets, the more complicated that problem gets, the harder it is to solve these at real-time rates. But again, we made a lot of progress on this, and we're inching closer and closer to that goal all the time. Okay, so what do we do with this? Again, this is now the kind of the application side of this, and like projects roughly that you might think about working on in the lab. We've done a lot of work on legged robots. The top left is showing like a cartoon simulation example of kicking one of these robots and having it flail around through the air and recover, and sort of work its way back to where it started. Again, that's all done automatically. That's all like emergent behavior from that setup that I showed you. You write down the cost function, you write down the dynamics, the physics, whatever, and it just works. You basically feed in the current state of the robot from the sensors, and like it just does this stuff. It's emergent. And so that's in sim. The lower right is showing that controller on an actual robot, which we finally got working last summer, and there's lots more to do there. So a lot of work on legged robots. The challenge here is actually reasoning about contact. It's the fact that the feet make and break contact with the environment makes this problem really hard because it's non-smooth. And so if you know anything about calculus and taking derivatives and all that stuff, when you have impacts, you have discontinuous dynamics. So there's like these kind of sharp things that are non-differentiable, and it makes all the math hard. So that's why this stuff's hard. We also work on a lot of space applications in our lab, and my background's in aerospace actually. And so a lot of our work is on lots of small satellite stuff that I'll talk more about. But another application we've worked on is satellite proximity operations, rendezvous, and docking. And this is an example of this from a couple of years ago where we worked on doing this on a pair of CubeSats, small satellites that we're going to dock. And the challenge here was that, number one, this had to be solved on board the satellites on very kind of tiny resource-constrained computers in real time. But also the thrusters had like a lot of limitations. The thrusters were cold gas thrusters with little valves that basically could only turn on and off. And they had limitations on how quickly they could open and close the valves. So this made the problem constrained in a weird way. Like you couldn't just get any thrust you wanted. Your thrust can only come in these kind of minimum impulse bit, they call it, like minimum basically amount of impulse because of the limitations on the valves. Kind of a weird problem. So we kind of figured out a solver solution to that could run on these guys. And we do a lot more of this stuff. In fact, we're doing more and more of this kind of prox-ops, rendezvous, docking kind of flavored stuff, and getting into now a really hot area is on-orbit servicing robotics. So trying to basically build robotic servicing spacecraft that can go up to old satellites and refuel them, repair them, upgrade them, all this kind of stuff. So that kind of mixes all these problems. It's, in space, it's involves contact and breaking contact with the servicing satellite, lots of uncertainty. It's a really hard problem. So we're doing lots of that now, which is very cool. Another NASA program that we've worked on for a bunch of years is precision entry guidance. So this is for like next generation Mars entry, descent, landing, for when they, we eventually send humans to Mars. We need to be able to try to pinpoint land in a way that we can't do now. It turns out actually the Mars landers, like the rover I showed you at the beginning, the error ellipse for those guys, which is basically the footprint within which we can put one of those on the ground, the sort of maximum error that we can target these things with, is actually sort of like 10 or 12 kilometers. We basically can only put something down on the surface within like a 10 or 12 kilometer circle, more or less, which sounds kind of bad. And so we're trying to figure out ways to make that better while also being really safe, right? If we're sending crew, we care a lot about safety and essentially not burning up. So you want to be both accurate and safe. And so that's a hard problem. It's hard because there's a ton of uncertainty in the Martian atmosphere. Like at Earth, we have weather forecasting and we know all this stuff, but at Mars, we don't have that. So things like the high altitude winds can vary a ton, the density can vary a ton. So you really don't know what the weather conditions, the winds and the atmosphere look like when you get there. And so you have to kind of try to figure that out as you're entering, and it's super hard to deal with that uncertainty. So that's kind of the way that's hard. Other stuff we've done stuff on cooperative control, like multi-agent stuff where you've got robots that are trying to team together to accomplish a shared task. And there's the challenges here is how you split up the control problem and get these robots to each kind of solve their own problem with their own dynamics and constraints and physics, while like communicating with each other to kind of sort out the collaborative aspect of the task. So this is kind of fun. That's us actually doing that, where these guys were all talking to each other over radios and coordinating this in real time. Similar idea, but distinct. We've also done a bunch of work on game theoretic control. So this is a situation. So the situation I showed you before, that was a collaborative, cooperative task where these guys were on the same team trying to accomplish a shared goal, and they were all talking to each other. But there's lots of situations where you need to interact with other robots or humans even, where it's not cooperative, where you don't know, you don't have communication with the other agents, and you're not necessarily on the same team. And the most kind of prevalent example of that right now that people care a lot about is autonomous driving, where you might be an autonomous vehicle, say like the blue guy here, and you're trying to merge in, and the other, say the green and the orange are humans, and you don't have direct communication. You're not necessarily cooperating, but you need to figure this out. And what we do as humans is we kind of like intuit, we kind of have a model, mental model for like what other human drivers are going to do and what their behavior is going to be like. And we take advantage of that. And like, for example, when you're doing merging on a highway and there's like not enough room between the cars for your car to fit, we kind of we've all done this, right? Where you like kind of nudge your way in there and force them to make space for you. And we kind of assume the other drivers are going to do that. So being able to reason about how you can influence the other driver's behavior, that stuff, you can model that as a game, a dynamic game with ideas from game theory. And so we've done a bunch of that and written, again, similar kind of solvers for these problems that can account for these game theoretic aspects where you're trying to reason about the other agent's behavior based on assumptions, assumed models of what their behavior is going to be, rather than having direct communication with them. And it turns out that works pretty well for stuff like this. We also spend a lot of time, I kind of mentioned some of the stuff like this, on trying to make these solvers for these kind of problems that are really efficient and they can run on embedded, like very resource constrained computing hardware. So in this case, this is a little crazy fly drone. These are about this big. They weigh like 25 grams, and they have a little microcontroller on them, just a tiny, microcontroller that's, again, very limited in its compute capability. And in fact, off-the-shelf solvers for doing this kind of stuff that we're talking about won't even fit in the memory on this microcontroller. So like if you tried to use a standard, algorithm for this, it won't even fit in the amount of RAM you have. So we wrote a custom solver that we call Tiny MPC. We actually just published a couple of weeks ago, that, as the name implies, is tiny and can fit in these it's super efficient and plays lots of tricks and is able to fit in memory on these really tiny microcontrollers where these off-the-shelf stuff won't even fit, and solve problems like this again. And we're running this at like a couple hundred hertz in this demo. You can do cool things with that. So it kind of embedded things on little systems. That also applies, by the way, to a lot of the space applications, because the computers, the radiation hardened computers that are available on these space missions are similarly resource constrained. So that similar kind of things apply, and you can't use a lot of off-the-shelf tools because they just won't fit. And then going more into the space stuff, we do a lot of work on attitude control, which is like pointing satellites. And we work a lot on these really tiny resource constrained satellites. We actually build satellites in the lab, and I'll show you some more of those in a sec. This is a CubeSat. These are about this big. They weigh about 1 kilogram. And it's these guys. So when we point these guys, we use actuators for this, some combination of, maybe thrusters, maybe these things called reaction wheels, which are basically little flywheels on motors. But all those take up space and mass and all this kind of stuff. And on really tiny satellites, you don't have room for them. So we spend a lot of effort trying to figure out other ways to do this attitude control stuff with other kinds of actuators. And what you're seeing here is actually using what are called magnetic torque coils, which are just electromagnets. They're just wire coils in the satellite that can generate a magnetic moment and then tug on the Earth's magnetic field, like a compass needle, basically, to generate torques to reorient the satellite. Super cool, totally solid state. There's no motors, there's no thrusters. They're just these wire coils, again, that are flat and super compact, take up no space. So there's just electrical power now that you need to do this, and you can fit this in a tiny box, and it's very cheap. So that's kind of a cool thing. Oh, sorry, that's the picture. That's a Torquil right there. That's what they look like. And this is kind of, the math for this, and, whatever. What else we got? So these are some of our satellites. This is a set of 4 satellites that we've built that we're going to be flying in around February 1st on the next SpaceX transporter launch. This is a mission called Pi-4. So this is showing you the satellites again. We've built a bunch of these. We do these missions kind of every year or two in the lab where we build small satellites. This shows you kind of what they look like in terms of size. These weigh about 2 kilograms, and they're about this big. And you can see relative to a hand there. Deployable solar panels, deployable antennas, you kind of see in the video, and there's 4 of them. And the mission we're trying to fly here is to do a bunch of like formation flying, mesh networking, relative navigation kind of stuff, where these guys are, again, going to like talk to each other and do some collaborative, formation flying kind of stuff autonomously, which is pretty cool. And I can talk a little bit more about some of the stuff that we're going to do here specifically. But so this is some of the hardware. And inside those satellites, the avionics, so like all the, kind of motherboard and all the electronics that make it all work. This is a project we've been running in my lab for about 5 years now. That's an open source avionics stack for these small satellites called PyCubed. That's pycube.org. You can go look it up. And the idea here is that traditionally the avionics that go into these satellites to make them work, they're super specialized and they're super expensive. And so if you want to like build your own little satellite as a university, capstone course, whatever, it's tens of thousands of dollars to buy this stuff. And it sort of doesn't need to be. And so we designed one of these. We've flown this on all our missions. We've radiation tested it, all that stuff. And we've open sourced it. And you can build these yourself for about $200. So if you want to build a satellite, go check it out. But also along with this is a software stack as well. So we've made these programmable in Python, and we have a whole Python-based software stack to do most of the standard things you would want to do on these. So it's very easy. It makes it easy to get up and running and kind of bootstrap yourself for these small satellites. So that's kind of cool. Lots of stuff to do in this kind of general area in the lab on the hardware side. And then what we're doing on PyCube, that kind of back to the control story, that's really cool and interesting. And again, playing into this whole like trying to do things cheap and small and all that kind of good stuff. We're trying to do formation flying with these guys. And normally what you do traditionally is use thrusters, but thrusters, you need propellant, and it's valves, and it's heavy, complicated, and expensive. And if we want to try to do this in these really tiny satellites at very low cost, you kind of can't fit all that stuff. So what we're doing here is using drag. So there is thin atmosphere up there where these satellites fly in low Earth orbit, really thin, but it's there. And by manipulating the drag on the satellites, so basically flying them kind of edge on versus face on, we can basically make, satellite 1 have more or less drag than satellite 2, that kind of thing. And we can use the drag to spread them apart and control the separation. So we can actually formation fly them using just drag. We had a recent paper on this too, where people have done stuff like this before, where intuitively by doing that, you can kind of put the brakes on, right, or speed up, and you can use that to spread out the satellites along track, like basically in a line along the orbit. But you can't really get any forces in the cross track direction because like drag only acts along the velocity direction. But we figured out a crazy kind of clever way of getting cross track separation as well that I won't get into because it's a little too complicated to describe in like 30 seconds. But it uses like some kind of next level, orbit perturbations and weird, clever ideas to basically get both that along track separation and cross track separation. So now you can not just do a line formation, you can do like a box or something more complicated and get 2 degrees of freedom out of this, which is very cool. Just with drag, so you still don't need propulsion. So that's kind of a game changer thing. And then another new project we've got going on, again on the space side, is doing vision-based orbit determination. So this is basically vision-based navigation for these little satellites. So the way we would traditionally do this, usually satellites on board don't really know where they are. They usually have to be told that from the ground, and we track them. They get tracked by radars on the ground, and then like we find out kind of their orbital state, and we uplink that. There's other ways to do this. You can, in theory, for low Earth orbit satellites, you can use GPS, but there's a lot of problems with that too. It turns out commercial GPS receivers don't work in space for a bunch of reasons. So you need like a custom GPS receiver to do this, and that's hard and expensive and bulky and power hungry. So GPS is also not a great option for these small satellites. But now, machine vision's come a long way. And this is kind of showing like roughly what you would see from one of these satellites if you had like a smartphone camera, like a selfie camera, like a very cheap camera. And then trying to do landmark detection with machine vision algorithms to pick out landmarks with known locations on the Earth, and then using that to then estimate your position and velocity and all that good stuff and kind of bootstrap that. So we have, again, another recent paper on this, doing just vision-based, kind of lost in space, figure out where you are, all that good stuff for these small satellites. So you don't need GPS, and the satellite can do it autonomously with cheap hardware and clever algorithms. Pretty cool. And yeah, I think that's kind of, again, this is a whole bunch of projects, hopefully that to give you some idea of what's going on in the lab currently. And all of these are things where we've already had risk people work on in the past, or we're super open to it, and they're kind of examples of things like the sorts of things you could get into over the summer if you were to come work with us. And that's our contact info, that's my email. That's our GitHub. We can see all the code for all the stuff I just showed you. And that's our lab website where you can see more info about these projects, and also all our papers are up there. So you can kind of look at some of that stuff too. And yeah, don't hesitate to reach out if you're into what we're doing and you're thinking about applying to RIS, and especially if you're into doing space stuff, if you like the small sat stuff, because we're kind of more or less the only ones at CMU doing that kind of stuff. And I'm always looking for people who are space nerds who want to work on that kind of stuff. But also if you're into the control stuff or any of it really, definitely drop me a line if you're thinking about applying, and I'll look for you at application time. And yeah, I think I'll shut up now and listen to you guys for a bit and take questions and all that good stuff.
Thank you very much, Zach. Yeah, for the awesome talk. Well, it's really cool. I think we can start the Q&A now, and I'll start with a question that I have. Whenever I see these space robots, the first thing that comes to my mind is the high degree of reliability that the systems need to have. And one thing that I was wondering is this something that you really have to worry about when doing the research, or it's treated more as an engineering problem when people are like actually implementing the ideas?
Yeah, so I would say like basically the short answer is we don't worry about it. There's when we build our own stuff, like the stuff I showed you where we actually build our own satellite hardware and all that, and we go fly them. For that stuff, we own it, we control it, and like we're taking the risk. And the stuff we've built and fly is all COTS components, like all kind of cheap, similar stuff to what's in like your smartphone, that kind of stuff, like consumer grade electronics. We test it a bunch, but I mean, there's nothing special about any of that stuff. And for stuff in low Earth orbit, I should say too that we're flying all this stuff in low Earth orbit. It's below the radiation belts, and the environment there is like pretty benign, relatively speaking. So it's not as harsh as if you go higher, farther away. And also the missions we're flying on these small sats are pretty short. Like the lifetimes of these are like a year or less. So all of that combined, it's kind of where you're flying them, and also the fact that they don't need to last for like a decade, like a Mars mission might, right? Like that we're okay with using consumer grade stuff. I mean, tend to not worry too much about it. We definitely aren't using like rad hard, like semiconductor parts and stuff like that. There are some like general kind of board engineering level things you do to like for reliability reasons, like you kind of do implement watchdogs and stuff like that. This is all stuff that's like at the like board engineering level or software level that we do. And most of that's really like there, not so much because the environment's like terrible and you're worried about radiation effects or stuff so much, but more just because like you don't trust your own code. And so like you want to, and you can't physically go and hit the reset button on the satellite, right? It's up there. You can't touch it. You can't go fix it. So having like writing code in such a way that you have safeguards and watchdogs that'll like automatically reset the thing if it hangs. And like you have the ability to upload code patches later to fix things, and like being able to download like kind of like code traces and debug logs and stuff like this to understand what's going on. Like you kind of want to think about it as, I need this thing to never, if my code hangs because I did something stupid, like I don't want the satellite bricked because I can't go reset it. So you think about that more, right? That's kind of really, it's usually us that's messing it up, not like it's not like the radio environment or whatever.
Yeah, that makes sense. Thank you. So next question is, does the lab have projects involving model-free reinforcement learning for lagged locomotion?
I would say like the easy answer to that is no. We're like, I don't know, this is maybe a bit of a philosophical thing or just kind of like the area we work in. We're pretty firmly in the model-based camp, whether that's like RL or optimal control, whatever. We like dabble in RL stuff and certainly like data-driven and adaptive ideas, but generally just like in terms of like the kind of algorithms we work on and like where we come from, like we tend to sort of like want to dig into the physics more and like do things that are, especially coming from aerospace, like there's a strong desire in that domain for things that are interpretable and safe. Like safety guarantees are a huge deal in these aerospace applications. So you want to like understand what the algorithm is going to do, understand all its possible failure modes, and like try to guarantee as best you can, be able to validate it and like guarantee that things are not going to like just sometimes randomly blow up on you for the reasons that we just discussed, right? Space is hard and all that. So I'd say there's a pretty strong bias away from these like model-free RL kind of ideas for these aerospace applications. And that being like my primary background and like, kind of where we do a lot of our work. I mean, that we're kind of in that model-based like optimization camp. That said, yeah, I mean, there's definitely cool things to do with these RL methods. We do stuff in that domain, but the stuff we go after in that domain tends to be areas at the intersection of like models and optimization and RL. So like, for example, like we're kind of dabbling right now in some legged locomotion stuff where we are taking we're using like an RL policy as like a high level, almost like planner policy thing. And then the low level, and then that thing kind of feeds into an MPC controller at the lower level that's actually doing like the torque control. And the cool thing about this is it makes it easier to train because the RL policy doesn't have to like relearn the dynamics or anything like that. And it's just spitting out references for the MPC controller to track. It also means that in principle, you can do zero-shot transfer between robots and stuff like this because the RL policy doesn't have to reason about all the details of the physics of the robot. And so you can just swap out the dynamics model, those dynamics constraints in the MPC controller that lives at the end of the RL policy, and just swap in some other robot's dynamics and stick it on another robot. So that's kind of a cool thing. So I think there are like pretty strong reasons that models are good. One is this transfer idea, right? If you want to go to a different robot, you don't need to train from scratch anymore. You just need to like, if you know the physics, you just write down the other model for the other robot and plug it in and go. And also, yeah, kind of these interpretability things. And I mean, it depends. There's pros and cons for all these things. But yeah, I would say we are pretty firmly in this like model-based optimization camp. And like, to the extent we do RL, it's model-based, and it's like in some broader context as part of some like, there's something else there. We generally don't do just model-free RL stuff.
Okay, great, thank you.
Very long-winded answer to a short question.
No, it was a great answer. I'm also very interested in this stuff, and so yeah, for me it was interesting at least, and I'm sure this answers the question. And this also touches on the next question, which is with the advancements in modeling dynamics through contact and mixed integer optimization, do you eventually see optimal controls technique to primarily exist in applications which need explainability or guarantees? Or do you think optimal control techniques will converge in some form of reinforcement or some form with reinforcement learning methods?
Okay, so yeah, I think like at a high level, like RL and optimal control are the same thing. They're just like, they're almost like, if I had to, like, this is a kind of me interpreting things, I guess, but they're the same thing. They're just different philosophies. Like they're not different fields at some level. They're like different people trying to solve the same problems who like have philosophical disagreements about, various aspects of how to attack those problems. Like they're trying to do the same things. And there's kind of the two extremes are like, model-free RL, where you don't want to know anything about the system or the physics, and you just want to like use data for everything. And then there's, classical optimal control, deterministic optimal control, where you know everything about the physics of the system and the environment, and it's super well characterized, and all that stuff, and you know everything, and that's it. And almost every real application is somewhere in the middle, where you know something but not everything, and there's unmodeled effects and noise and blah blah blah. And then it's just a question of where you are on that spectrum. That's like, you're doing the same stuff, right? At the end of the day, like the optimal control problem I wrote down, that's the same problem whether you're doing RL or optimal control. The only thing is like how much of that model you think you know. And like, and then it's the same problem setup. It's just, again, like how much of that model you assume, and then what algorithms you use to solve the problem. It's really the solution algorithms that are different between RL and optimal control. And it's a lot of the differences are more philosophical than like real. And it comes down to, again, like how much you want to assume about things and how much you want to like write down a priori versus learn from data. And there's a huge middle ground. And like this, again, like, and these things have been around forever. It's not like this is a new thing. Like if you go back 20, 30 years, like a lot of what's now called, reinforcement learning would have been called adaptive control. And people have been doing this forever. So like it's kind of like, so I would suggest, like, I think basically like there's these two camps, but it's in my opinion, a very artificial distinction. It's basically people who came up through computer science versus people who came up through like mechanical, electrical, aerospace engineering. And like, it's more a philosophical divide than an actual real separation between these. They're not really two different fields. That's my take. And like, we kind of need to bridge those gaps, and the gaps are more artificial and like philosophical and like by like historical accident of like what department someone got their undergrad degree in versus like, anything real. And so the more you can like learn about both sides of these things and really understand that, and bridge those gaps, the better, because there's good ideas from both camps and we need both sets of things. And if you're going to go be a good engineer and try to make a real system work, you want to just do the right, use the right tools for the job and not be married to one of these things or the other for stupid reasons, right? And sometimes if you know everything, if you have a really good model and like this, dynamics are pretty clean and there's not a lot of noise in your sensors and stuff, then like the model-based stuff works really well and is really good, and you should probably do that. If on the other hand, you have a situation where there's like, huge uncertainties and you can't model all the physics for various reasons, and like, I don't know, there's lots of noise and like it's not, nice and Gaussian, but super weird and time varying, like then like it's really hard to write a model down. You probably want to do something data driven and maybe something more RL flavored. And there's a huge middle ground in between. And like, depending on where you are in that spectrum, like ideas from both can be useful, and you should know all of that stuff, and you should be able to pick and choose which pieces are the right ones for the problem you have, right? So that you should know all of that stuff and use whatever is the right tool.
Yeah. Well, thanks. This is a very interesting perspective. Yeah, indeed. So one more question. Recently, combined approaches of using ML for optimizing control problems have gained traction. Is this something the lab is interested in exploring?
I think this is roughly the same question as before. Yeah, like we do use like machine learning stuff in all kinds of places. Like for example, the vision-based navigation thing I showed you, that's all machine vision stuff, right? There's like a big neural network in there, and all that good stuff. We also have like RL flavored projects that we've worked on. Like, again, I think there's a huge continuum here, and there's no, like, I hate this like black and white distinction between reinforcement learning and optimal control. They're the same thing, and it's just kind of, and it's a very gray kind of like continuous spectrum between them. And so, we probably live more on one side than the other, but like, versus some other people, but like, we're always somewhere in the middle there. It depends on what you're doing.
So next question. Do you see the lab working on any optimal control problems for contact-rich manipulation, or will most of the projects focus on space applications?
Yeah, no. So we actually, in fact, I just gave a talk last weekend at an IROS workshop called Models for Contact-Rich Manipulation. I didn't talk about it, but we have an ongoing project right now. One of my students is currently working at Google doing manipulation stuff, and most of that centers on. So I teased this a little bit for some of the locomotion stuff. We've spent a lot of time worrying about contact physics and how to model that stuff and how to differentiate through it, like differentiable simulation, all this kind of stuff. And obviously, one of the other big applications for that is manipulation, and we've been doing quite a bit of work in that area recently, mostly around how to reason about like contact geometry and like. And then how to do like planning control in sophisticated ways while we're using about all this stuff. So yeah, we have a bunch of stuff along these lines too. It's a little newer and like a little bit less published, which is why I didn't talk about it too much, but we're pretty actively working on this stuff. We have again, there's this workshop a couple of weeks ago at IROS where we presented some of this stuff, but it hasn't been published yet in a full paper. So we don't have a ton of stuff, but we're definitely working on that. I'll tease. The stuff we talked about at that workshop was trying to use point clouds directly in your simulation to represent the geometry of the objects. The reason this is cool is that we've got point clouds, like a lot of our vision sensors spit these things out natively. And right now, like if you're trying to like, look at the world and like reason about objects and how to grasp them, we don't really have a good way of doing this. So we have like a really cool, I mentioned, contact, collision geometry, all this stuff. We have some really nice ways of computing collisions between points and convex primitives. So like you have a box or something and a point, we can do that really nicely. And if you have a point cloud, it's just a bunch of points. And it turns out we can parallelize this really nicely on like a GPU over the points in the point cloud. So now if you just get a point cloud and you've got like, I don't know, a few thousand points to represent, like if you have some really weird shaped object, right? Point cloud's a pretty nice way to represent that. And so you can just take the point cloud as is and basically shove it into your physics simulator and do motion planning on top of it to do like grasp planning and all this kind of stuff, directly reasoning over the point cloud. And you can throw it on a GPU, so it's really efficient to query that, all that kind of good stuff. So we're doing a bunch of stuff like that right now, which again is very recent stuff, still ongoing work and not really published yet or ready for prime time. But yeah, there's definitely stuff along those lines that we're into. We're very into contact stuff generally, I would say.
Yeah, so yeah, I advise the students to keep an eye on the ROS workshop, maybe when it gets
published.
Yeah,
I think the workshop, you can find it. It's something like, models for contact-rich manipulation, something.
Okay.
And the little workshop, talk and paper and stuff is on there. And you can find our stuff there. There's a little like 4-page extended abstract on the point cloud stuff that I just mentioned.
Oh, great. So next question is, I'm very interested in space robotics, but the aerospace program in my home country is not as nearly well developed as in the US, so we don't find many opportunities here. What would be example of accessible but meaningful in the sense that I would learn interesting things, projects you would suggest I could work on?
So if you mean as part of the RIS program, if you like came and visit us for the summer, I mean, pretty much any of the stuff I just talked about, you could jump in on. We have multiple ongoing smallsat projects, CubeSat project, et cetera, that you could be part of. And anything from like kind of hardware engineering stuff, like working on, boards and electronics, avionics, sensors, stuff like that, all the way to like, GNC, guidance navigation control algorithms, like the stuff we talked about, like the VisionBased, navigation stuff, or like any of those control things, attitude control things, like all of that's kind of on the table. We do all that stuff, kind of the full spectrum from like pretty in the weeds hardware up to like the autonomy algorithm stuff, the full stack. So pretty much anything in the stack, like we have projects in the lab and you could get involved if you were to come hang out with us.
Great. Next question. Regarding generalizability of control frameworks across different robots, how does the lab approach this challenge? I think you kind of mentioned this when you were talking about the models, right?
Yeah, I mean, I think basically my take on this is why models are good. If you do model-based control, then like the algorithms work on anything you can model. So like if you have a new robot, you get a model of it and you plug it in and your algorithm still works. So like this is hugely powerful. This is why model-based control, honestly, like probably more than any of these interpretability things that people like worry about, stuff like this. Like one of the major advantages of a model-based controller is that it is generalizable. It is very, very generalizable in ways that model-free learning-based approaches just never will be able to do. And I was getting at this, this like idea of like zero-shot transfer. Like if I have a new robot, as long as I can write down a model, I can just plug the model in and the controller works on the new robot. So if you want to change anything about the parameters of the robot, like it's easy. I just stick the numbers in and I have, change my model a little bit, still works. So that's hugely powerful. And like we take advantage of all this time. And this is actually one of the reasons we're interested in like hybridizing like model-free RL policies with like model-based, like MPC controllers, where you'll basically have the RL policy reason at a higher level, like a slightly more abstract level about behaviors and stuff like this, and spit out like, rather than control commands or torques or anything like that, spit out like a state, like a snippet of like a state trajectory, like a motion primitive or something will come out of the RL policy. And then we'll take that out and track that with an MPC controller that has like a model of the robot's dynamics available to it. And this way you can train this RL thing like on a very general kind of, do all the domain randomization on like all kinds of different quadrupeds, for instance, right? With all different kind of parameters, whatever, to be very general and reason about like at a slightly higher level. And then you can just plug in whatever model of whatever specific robot you have into that MPC controller, and the thing will just transfer to any of these robots. And you can tweak the robot setup and tweak the model, and it still works, right? So I think that's a huge win for models.
Oh, great. Thank you. So one more. What mathematical background do you think is most important for working in optimal control? Convex optimization, simulation techniques, or another thing, anything else?
Linear algebra. But yeah, if you already know, if you know lots of convex optimization stuff, you're already like definitely a leg up and ahead of the game. Yeah, like I would suggest like you gotta like be pretty good with your linear algebra chops generally, and like all the other stuff you can pick up. But yeah, certainly if you like know a bunch of convex optimization stuff, that is super useful. Like basically for like incoming PhD students, I basically tell them like they should take a convex optimization class. And like that's one of the most important things. There's definitely other things like that are important. I think like we do a lot of physics-based stuff. Other stuff that's again back to the linear algebra, like a linear systems class is really helpful. And yeah, like I mean, we do lots of physicsy stuff. So having like at least like some kind of like upper level undergrad like level of dynamics course is helpful too for some of the stuff we do, but it depends on what you want to get into, more specifically. But yeah, I would say like being good at linear algebra and like the convex optimization stuff is probably the most useful stuff.
Okay, great, thank you.
But not that there's like a real hard prereq on that either.
Okay, yeah, okay. Now shifting to questions more related to applications, grad school applications is, are there any requirements or tips for aspiring MSR students interested in the REX lab?
I mean, I think like I don't really have any like super concrete tips on this. I think like so high level tips about like generally, like applying to our lab or anywhere else. Like I think like, people say various things. I get too much email, but like it never hurts to reach out. Just try it. You might not get a response, but you might. And like, who knows? Like that's not a bad thing. One thing I will, even if I don't respond, like when I go look at applications, I will probably go search for names in my inbox to see if people have reached out to me, even if I didn't respond before, and see if they like at least like took that step. Like I think that doesn't hurt. You'll hear different things. I don't think it ever hurts you, and like it, worst case it does nothing, but like it's not going to hurt. I used to respond to all of those, but as my inbox has gotten worse and worse in the last couple of years, I've now like really tapered off. My inbox is terrible. I apologize for not responding to all of your emails, but I used to try hard at least, and now it's gotten ridiculous and I just can't keep up. So I don't respond to a lot of things, but I certainly don't mind it. It's not going to hurt you. And like, I do still try to respond to them, and I will go like search my inbox for sure at application time and see if you've messaged me. So yeah, that, I think like the best thing too, is like really if you get the chance to go to a conference, like if there's a conference near where you live, or you're able to go to like, again, like IROS, ICRA, these kind of things, whatever, and just meet people face to face. And that kind of thing is super huge. And there are like all kinds of, if that's hard for you to do, like there are travel grants available, and the conferences do these themselves. There's various organizations that have these, but like getting the chance to go to a conference where the kind of stuff you're interested in, if it's robotics writ large, then like ICRA and IROS are kind of the big ones, right? But yeah, anything like going to one of those conferences, seeing what like people are doing, and then like trying to get FaceTime, like just introduce yourself to people. This is also like a huge thing that's super valuable to kind of calibrate and see what's going on, and also to just put a name to a face. This kind of thing is great. Yeah, and then if you're gonna reach out to people, like the other thing you should do is like you should be familiar with people's work. Like if you're gonna email me, or if you're gonna like apply and say you want to work in my lab, you should go do your homework and like at least read a few of our papers from the last year or two and know what we're doing and have like something intelligent to say about it, like you should look like you did your homework, right? Like if you just email me and say, oh yeah, I'm interested in deep learning and machine vision, which I get emails like that all the time. It's like, we don't do that stuff. Like we're not a, deep RL machine vision lab. Like you clearly don't know what we do, and you're just like blanket emailing me because you like Google CME robotics and saw my name on a list. Like don't do that. Like that will hurt you. So like if you're going to reach out, like make sure you did some homework, you know what we do at a high level, you know like what projects are going on, and you can say something informed about like, oh, I think this project's really cool and I'd love to get involved in this because blah, I don't know, something like that, right? That makes it look like you at least know what you did, some homework, and you know what we're about, and you have something informed to say. Like I think, yeah, that's probably all I've got. That's a pet peeve. Like I do get emails all the time, like I want to do deep learning, and I was like, yeah, no. So don't do that. But yeah, I don't know. It doesn't hurt to reach out, do your homework before you do it. Try to go to a conference. Yeah.
Apply to RIS.
Apply to RIS. Yeah, RIS is awesome. RIS is, I think, is an awesome program, and like really sets you up well to like as a springboard into grad school applications. Also, they do an awesome job of like guiding you through that process, giving you lots of advice. And yeah, like when another big thing to do if you're applying, if you're RIS is awesome, you should do it. But if you're just like talking about applying to master's programs, PhD programs, ask your friends, like just find examples. Like if you have any friends that have done this in the last couple of years, if you know anyone who's applied in the last couple of years successfully, like go ask them to share their application with you, and just do as much of that as you can, and look at as many examples as you can to get calibration on like what they're supposed to look like. That's kind of the other advice.
Yeah. Well, and I can also add that we are hosting with some students from the RI, hosting 3 webinars this week with grad school application advice. So if you're interested, you're welcome to join. We'll have one at 7 p.m. EDT tonight. So yeah. Last question before we wrap up is, you mentioned the first example of animals in nature outperforming our current robots. So how do you think robotics can use bioinspired design for developing better control systems?
Yeah, I mean, this is a super interesting and like very, very like broad area. There's a lot of people doing like bioinspired robotics and this kind of stuff. I would say like we kind of don't do this sort of thing. We don't do a ton of like design. I have like one student who's interested in design optimization and this kind of stuff. So we've like dabbled a little bit, but we're not really like, that's not kind of our main thing for us. I think it's super interesting. I like the aspect of it that I'm particularly interested in is like this idea of co-designing, because we do controls, right? We're control people, but like this idea of like co-designing controllers and robot morphology or like robot like design. Like you really want to co-optimize these things, right? There's tons of interesting examples of this, like and relatively close to home example for us is legged robots. There's been like a ton of like last couple decades people looking at like series elastic, parallel elastic actuators, passive compliance and stiffness in the legs and stuff like this on legged robots. And there's analogies to like Achilles tendons, right? For us and in like the way that our legs look and our ankles function when we run and stuff like the idea of like passive energy return and something like an Achilles tendon. You could build a series spring right in your leg, and the Cassie robot and Atreus before that did this kind of stuff. So people have looked at this for a long time, but I think that's super interesting. And there's this really like kind of interesting interplay there between what is the passive dynamics of the robot going to do versus what are you going to do with a feedback controller. And the line is very blurry, right? So like this idea of having a series elastic spring, well, like that's putting in this like kind of passive stiffness in the leg joint, right? That's equivalent to having a proportional controller running on my motor with the same stiffness, right? I could do that with an impedance controller, just the same. I could get the same physical response, right, out of the controller or out of the hardware. So I think there's this really, and what that does now, the controller, in principle, the controller is way more flexible, because if I want to change that spring stiffness, I can just tweak a gain in the controller and I can have it be equivalent to any spring I want it. Whereas if I build it into the leg and the hardware, I can't change it. So like there's like there's a weight penalty maybe with doing it with a physical spring versus in the controller, but there's also maybe an energy penalty to doing it with a motor as opposed to the passive spring, right? So I think that's a super interesting thing, right? Like, and this idea that like there's really an equivalence between some of these like physical design ideas and like control ideas. And it's not always clear cut which one is the right choice. I think it depends a lot on the application. Like if you want to, for example, with a legged robot, if you want to run super efficiently, you can make a passive runner that almost can just run passively, like, and you just need a little bit of control to like keep it, from falling over, like just, balancing control and a little bit of energy recovery in there to like handle losses due to friction and stuff like that. But it almost will run on its own. But all it can do is run in a straight line at the same speed on flat ground, right? And so that's the trade-off. You could make something that like mechanically was super dialed in for one specific use case that's uber efficient and all that kind of stuff, but it's super limited because it's all baked into the hardware. Whereas, on the other extreme, you can do it all with feedback control, and now it's super general and it can do all these different tasks with a really complicated controller, with like really kind of generic hardware, but it's going to be super inefficient. And that's actually more the norm right now. Like if you look at current humanoids, for instance, they tend to be like really energy intensive, like really energy inefficient, and can only run like unplugged autonomously for like 20 minutes maybe before they run out of juice. They're like, if you look at like the energetics of walking for like a big humanoid robot, it's terrible. Like it's way, way less efficient than like you and me. And because we have the passive stuff, we have like, the Achilles tendon stuff doing passive energy return. We don't have to use our muscles a whole lot for a lot of that stuff, all this kind of good stuff, right? So I don't know, that's a super interesting space. We do not as much of that stuff as maybe we could or should. And I'm definitely interested in it. There's lots of cool stuff to do. And again, the angle on it that I'm really into is this idea of like co-design of controllers and passive physics, and like what combination of those two things like is right for a given situation, I guess, or robot design or application. Again, another long-winded answer.
Awesome. I think we can wrap up here. Well, thanks for the amazing talk and for the awesome work. And for making time for us and for the students here. I'm sure they'll benefit from this. So I guess this.
All right, cool. Yeah.
Well, take care. Bye.
Bye.
Any additional comments?
Yeah, don't be afraid to reach out. Do your homework, send me an email, apply to risk, and again, we're always looking for students for risk. We always take, at least one, usually I'm happy to take multiple risk students, and it's mostly about the fit. Like, are you interested in what we're doing? That kind of thing. And especially if you're interested in any of these space topics that I mentioned, like if you're into small satellites, definitely like get in touch. We're always looking for folks who want to work on that kind of stuff. But yeah, the control stuff in general, if you're into model predictive control and you haven't totally drunk the model free RL Kool-Aid, that's good too. But yeah.
Awesome. Thank you very much, Zach.
Right.
Yeah.
Yep.
Take care. See ya.